Good afternoon to everyone. So we'll discuss, I will talk today about egress protection, fast egress protection. That is a joint project that we've done at Deutsche Telekom. So we started a couple of years ago, actually, and now it's in full production. So the current status of the draft is that the draft was issued last year, 2016. And the first version of the draft, and now, as you see, this slide is not very accurate because we have the version 6 already of the draft with support from Juniper, Deutsche Telekom, Huawei, and as well Orange. So Orange as well joined us in supporting the draft. So let's start. Okay, before I discuss the egress protection, I discuss the architectural model that we're going to cover here in this egress protection. So basically, when you have a very big network, you typically divide these big networks on smaller pieces, like some IGP domains, areas, or maybe autonomous system. You have member autonomous system, confederation, something like that. So at the end, this is more or less the picture of your network. How does it look like? Okay, it's divided in different pieces. And in this network, every node has different function. So we have access node at the axis of the network. Yes, access node is connected to some what we call here ingress node. The ingress node is the ingress node on each domain. Okay, so because we have many domains, many IGP areas, we have many ingress nodes from that perspective, from this end-to-end protection terminology perspective. And then we have transit nodes. So transit nodes, there are some nodes inside of each domain. And then at the end, we have egress nodes. So egress nodes, this is at the end of each domain. And for each of these node types, we can have protection. Yes, we can define ingress protection. What we say ingress protection, this is basically the access node is trying to protect themselves against the failure of the ingress node. So it's when it detects the failure of the ingress node, it switches over to another ingress node. This is ingress protection, this terminology. Then we have transit protection. Transit protection is against the failure of the transit node and transit links. And we know that it's covered by LFA, for example, remote LFA, topology intervented LFA. In RSVP world, we have RSVP fast reroute or RSV one-to-one protection or facility protection. So a lot of different applications or different protocols we have here to protect ourselves. I will not cover this part of the story. But we have as well the egress protection. So egress protection is against the protection against the failure of the egress node. So we can define, let me go to the picture, the primary and backup egress node. Okay, so here on your right side, you have primary egress PE and backup egress PE. And you would like to protect the traffic against the failure of the primary egress PE. Okay, so how can we do that? So we can, for example, on the ingress node, so on the left side, on the ingress node, we can pre-install in the FIB, in the forwarding table, the next hops to the primary egress node and backup egress node. Okay, this is one of the options that we have. This is called the BGP peak edge, by the way. Okay, so a BGP peak edge function, and it works. Okay, this is implemented in the noise network. It works. The problem with this BGP peak edge is that it's called peak edge, which means prefix independent convergence. It's independent from the number of BGP prefixes, but not really independent from the number of IGP prefixes. Why? Because you need to detect, the ingress PE need to detect that the primary egress PE failed. Okay, how this detection happens? Because only after this detection happens, the ingress PE can switch over the traffic to the backup egress PE. How this detection can happen? There's similar ways to detect this failure. One of the ways is global IGP convergence. Okay, so from the global IGP convergence, eventually, ingress PE, we realized that the egress PE failed. What does it mean, global IGP convergence? It depends on the size of the network. Okay, depending on the size of the network, if your network is small, it's a couple of 100 milliseconds, but if the network is very big, if your IGP domain is very big, it can go up to 1 or maybe 2 seconds. And this is reflected then later in the BGP peak edge failover convergence. Okay? Then even more convergence you can expect if you have a network topology like here on the picture, yes? If you have divided your network in some domains, interconnected these domains with BGP labeled unicast to have end-to-end LSP, etc., you have even more. So your information that the primary egress B failed need to cross many, many domains. And of course, it would take some time. Okay, so it's not immediate. So you can improve that by running BFD. Okay, when you run BFD from the ingress PE to the egress PE, of course, you can more quicker, or you don't depend any longer on the IGP convergence to detect the failure of the egress P node. You depend on the BFD convergence or in the BFD timers, yes? But in very large networks, it can be as well challenging to have aggressive BFD timers for large number of PEs. And we are talking here about large networks. All right? So, I discussed already that. So that's the reason we are introducing a new way of doing egress protection. Okay? Basically, the new way of doing egress protection is we shift the duty to restore the traffic or to switch over the traffic from the ingress PE node to some node which is closer to the egress PE. And this node is point of local repair node. It is directly connected to the egress PE node. All right? And this node, the task of this node will be to switch over the traffic to backup PE node. So this is the basic idea. So the backup of primary node will restore the traffic. What we introduce here something that is called context ID. Context ID we could imagine as some kind of virtual loopback that is used by BE when the VPN prefixes or the service prefixes are advertised. So normally when we advertise the service prefix, we are using loopback, okay? Here, instead of using loopback, we use this kind of virtual loopback, we call it context ID. Why we use that? Because later on, later on, we'll advertise this virtual loopback or this virtual context ID from two PEs, from two egress PEs. And because of that, we'll be able to do LFA or remote LFA. So we'll be able to do switch over inside of the network to another PE. So this is the context ID. Then we are introducing as well a function that we call protector. So what is protector function? Protector function, so you could imagine when you do the traffic restoration for VPN, it is not enough just to switch over the traffic to the backup PE, because this traffic will eventually arrive to the backup PE with a label which is allocated by the primary PE. Okay, so the backup PE needs to be able to handle this traffic. In order to handle this traffic, we actually send the traffic to something that's called protector. And this protector will translate the VPN labels from the VPN labels allocated by the primary egress PE to the VPN label allocated by the backup egress PE. Typically, the protector is configured on the same node as the backup egress PE. So let's discuss on an example. Okay? So this is again our network, our big network. And let's focus on the egress side of these networks. Yes, we have traffic which is flowing from the left to right side. On the right side, as you see, you have two potential egress P routers, primary and the backup, because C on the right is connected to two routers. So let's focus what's happened here. So this is in the normal state, the traffic from left to right. Yes, it's traffic entering CE on the egress P send the traffic to the primary egress P, and the traffic is going to the CE on the right side. All right, now we start to prepare our network for egress protection. So as I mentioned, we will be using as the next hop in BGP updates something that is called context ID. And this context ID is injected into IGP in the primary egress PE. There are different methods how we inject this context ID. I will not cover these methods because we have not enough time. But let's assume that we inject this context ID with some very good IGP characteristics. So for example, this is my context ID 1.1 with a metric 1. Okay, so low metric. Now at the same time, the backup egress P or protector backup egress PE advertise the same prefix. Okay, injects the same information, but with bad IGP characteristics. For example, here it could be some high metric. As I mentioned, there are a couple of ways how we do that. I will not cover that because not enough time, but this is an example. Okay, so what does it mean? It means that later on inside of my network, I will see this prefix being injected by 2 PE nodes. And if something happens in the network, I can do, for example, LFA to redirect the traffic, yes? Because the traffic will be going to the 1.1. If something happens, I can redirect the traffic. So based on this information, as mentioned, so PLR will be able to build the LFA, for example, FIP structure, or RSVP, UF as well, RSVP, and not covered here, but LFA, for example. Okay, so primary next hop on PLR will be P1, and the secondary next hop, or backup next hop, will be P2, based on normal LFA action. So nothing special here is required on PLR. All right, in the next step, both P1 and P2, they advertise the service prefixes, VPN prefixes. Okay, we have some CE connected to P1, P2. This CE advertising some prefix 10/8, and this prefix 10/8 is advertised from P1 and P2 to some rot reflector. Okay, and rot reflector advertises this prefix to every PE. So eventually, this prefix will arrive to ingress PE, and as well, P1 and P2 we exchange the prefixes as well because we assume that we are using different rot distinguisher, which means every PE will receive the traffic. And what is special in this advertisement is that the PE advertise the next hop of this prefix as this context ID, 1.1. So not the local loopback. So usually it will be local loopback. Yes, normal case would be local loopback as the next hop. Here, instead of the local loopback as the next hop, you are advertising 1.1. Right? So prefix advertised by P1 go to rot reflector, and from rot reflector it is reflected to P2. So eventually, P2 receives the prefix, the service prefix or VPN prefix from P1. And P2 is configured as the protection function for 1.1 next hop. Okay, so every time when P2 receives some VPN prefixes with 1.1 next hop, he knows, okay, I am protector for this guy, for these prefixes. I need to prepare my FIP and RIP to be protected because eventually, what does it mean protector? It means that eventually, when something happens in the network, the traffic will be redirected to me with the labels allocated by P1, okay? So for that reason, step 5, P2 creates internal RIP and FIP structure in order to be able to handle the traffic that will be eventually redirected. Okay? Later on, I have some slides how this RIP FIP structure looks like, but the point is here that the traffic that will arrive to P2 will have the VPN label allocated by P1. Okay? And P2 needs to be able to handle this traffic with the label allocated by P1. Step 6, traffic starts to flow. And it flows normally over the LSPs to ingress to primary egress P to P1. Okay, because the next of Y flows to P1 because the next of Y.1 advertised by P1 has better IGP characteristics. The same next host is advertised by P2, but it's not so good characteristics, which means that, of course, everyone prefers to send the traffic to 1.1 in the direction of P1. All right, traffic is flowing, very good. And now, some failure happens on P1. Okay, P1 failed, line count failure, for example, or complete failure of P1. The traffic still flows. Ingress P still doesn't know that something happened. Okay, so ingress P still sends the traffic over the same LSP as previously. This traffic eventually arrives to PLR. PLR is the node directly connected to P1. And PLR already knows that PLR is dead because the link, for example, to PLR went down. So what PLR does, it uses the backup next hop. Yes, we discussed PLR has prepared LFA backup next hop, for example. Okay, so PLR is using backup next hop and is redirecting this traffic to protector. All right, when the traffic arrives to protector, I didn't mention before, sorry, when the protector advertises this prefix 1.1 into IGP domain and LDP eventually, it uses a special label, it uses exact label, not implicit null, because normally we are using implicit null or explicit null, so label 3 or 0. Here he is using some explicit label like 20, 25, 26, whatever. And later on, when traffic arrives to the protector, it will arrive with this label 26, for example, and protector knows that this is the redirected traffic that originally was destined to P1. Just one question.
Yes, Jacob Heights from Cisco. You said when the line card fails on PE1, this happens. However, PIC will still, edge PIC will still protect if a line card fails on PE1, even towards the core.
Yeah, when the line card on when the link between PLR oh, line card, okay, line card, yes, but the entire node, for example, when the node fails.
Yeah, the PALV has to fail. The whole PE1
yeah,
has
whole
to go
PE,
down.
exactly.
Then you're right.
Exactly, yes, you're right, yes, you're right. Yes, because for the link only on line card, we could redirect the traffic, yes. But entire node. Yeah, this is not protection, so egress not protection. Okay, when I was here that, so traffic arrives, redirected traffic arrives to protector. For example, with this label 26 that was allocated by protector, and protector knows that this is the redirected traffic, so this is not the normal traffic that the backup P normally should receive, but this is redirected traffic. And then he's using this RIP FIP structure that was prepared before to handle this traffic and to send to the local CE. And then eventually, of course, ingress P, we realize that failure happened, and we'll start to send the traffic directly to the second PE over LSP directly to the second PE. Okay? That in very large networks that can take some time. All right. So overall, in protector functions, so this works regardless if we are using LDP or SVP. So SVP as well is prepared. So SVP with facility backup, so node link protection. And protector binds the real label, this context ID label, we call it, to some special RIP FIP structures in order to translate the labels. Yeah, because we could have two options to place the protector, something that we call centralized option, which means that the traffic is redirected to the protector. Protector makes VPN label translation and send the traffic to the backup P. So the separate protector router and separate backup P router. Or we could have another option, which is combined protector and backup P, that the traffic is redirected to this combined protector backup P, and simply instead of doing VPN label translation, this combined protector backup E sends the traffic to the CE. And here's some example of the routing table structures that we have. So basically, first we have MPLS FIP, yes, so MPLS table. In this MPLS table, we need to check, so when the packet arrives, it will have some MPLS labels. Okay, so first the packet is checked against this MPLS table. In MPLS table, I realized that packet arrives with 26, for example, and then it means it needs to be looked up in context ID MPLS table, the second table, this 10.1.1.1 underscore MPLS.0. This is second MPLS label. In this MPLS label, I have the labels collected from P1. Okay, this is not my local allocated labels, but labels allocated by P1 that I received. How I received these labels? P1 advertised VPN prefixes to rot reflector. Rot reflector reflected the prefixes to PE2, so PE2 knows the labels allocated by P1. Okay, and it stores these labels here. And then, so the second label, in the second table, the lookup for the second label, which is the VPN labels allocated by P1, is done. And then we have IP label, based on IP label. This is for the next hop and the VRF. And then you have backup P function locally, then we have VRF label table. So this is basically how does it work. I have some couple of examples, show outputs. Yeah, so here, for example, I was mentioned before 26, so this is this label 301 something. That is the context ID label that was allocated by PE2 to protect next hop 1.1, basically. Okay, traffic arrives here, I remove this label, I am doing lookup in the second table. The second table is the table that is collecting the MPLS labels from P1. All right, I remove the label, and then there's an IP lookup normally. If I have locally connected CE, so I am combined protector and backup PE, then I send the traffic directly to CE. All right, so conclusion here. So the idea here is that this protection is moved from the ingress PE, as with BGP peak edge, to some node which is very close to the egress PE. Okay, and because it's moved to the node which is very close to the egress PE, the reaction can be much faster, because we don't need to wait for the convergence, IGP convergence, for example, to redirect the traffic. Okay, and because of that, we can provide sub 100 millisecond protection regardless of the AGP scale and BGP scale. BGP peak edge still depends on the IGP scale, typically. Okay, also there's no requirement for large-scale BFD with aggressive timers. So we discussed that we could eventually run between PEs. We could have BFD sessions to detect the PE failure. And first deployment started a couple of years ago, and one of the Deutsche Telekom networks now is fully functional and is working very well. Right, thank you very much. That is all I wanted to tell. Are there any questions?
Philip Matthews, it seems to me that your solution could be solved. I mean, there's an existing solutions for your case, I mean, which have actually fairly widely deployed. For layer 2 services, it's called active standby pseudowires, and for layer 3 services, you can use add paths.
Right, but it still depends on the time that ingress PE realized that the egress PE failed.
Sure, but
yeah.
You can use BFD or something like that.
Exactly,
yes. BFD to solve that issue.
Yes, you can use BFD, and depends on the scale, yes. This is what I mentioned.
And you don't have to go all the way back. You can just keep that all within a single AS, too. You don't have to go back to the original AS.
Well, ingress P need to realize. If you have large network in multiple ASs.
No, if you split across 2 AS, you can just isolate the knowledge of all this stuff within a single AS. You don't have to have it cross AS. You can come in, you can do the top path for the first AS and then drop to the bottom, effectively drop to the bottom path for the second AS.
But then you need to have service stitching.
Yes, but you probably have something like that between the ASs anyway.
Yeah, there are different options, yes.
Any more questions? All right, well, thank you.
Okay, thank you very much. Thank you.